The cosmos hides its greatest secrets in plain sight. What if the most enigmatic objects in space were not born from dying stars, but from the violent birth of reality itself? We are talking about primordial black holes, theoretical remnants from the universe's first second. In this journey, you will discover 25 mind-bending theories that connect these ancient relics to the biggest puzzles in modern physics. By the end, you will see the entire cosmos in a radically new light. We will investigate if they are the invisible dark matter holding galaxies together, and if one could be lurking in our own solar system right now. What single cosmic mystery do you most hope these ancient objects will solve? The very fabric of our universe is missing something monumental. For decades, scientists have known that the gravity holding galaxies together far exceeds what the visible stars and gas can provide. Something invisible, something that does not interact with light, must be woven through the cosmos, a ghostly scaffold known as dark matter. But what is it made of? One of the most compelling candidates are the very objects born from the universe's first chaotic moments, primordial black holes. Think of the infant universe not as a smooth, expanding balloon, but as a pot of water at a furious, rolling boil. In that seething energy of creation, pockets of space could have collapsed under their own intense density, instantly forging black holes. Unlike their stellar cousins, these primordial ones were not born from dying stars. They were stamped directly into the fabric of spacetime from the beginning. This means they could exist in a staggering range of sizes, from smaller than an atom to more massive than many stars. And because they formed so early, they could be everywhere, drifting unseen through galaxies in unimaginable numbers. Their sheer abundance and their gravitational nature make them a perfect, elegant solution to the dark matter puzzle. They are the invisible mass, the cosmic anchor we have been searching for. Of course, not every size is possible. Observations have placed strict limits, ruling out black holes of certain masses from making up all the dark matter. If too many were as massive as planets, for instance, they would warp the light from distant stars in ways we do not see. This has narrowed the search to specific mass windows. Some of the most promising candidates are primordial black holes with masses similar to a large asteroid, or even planet-sized behemoths. The hunt for these unseen giants is on. Astronomers search for them using a phenomenon called microlensing. If a primordial black hole passes directly in front of a distant star, its gravity will act like a lens, bending the starlight and causing the star to temporarily brighten. We are also listening for their collisions. When two of these ancient objects spiral into each other, they send ripples through space-time, gravitational waves that our observatories like LIGO and Virgo can now detect. Each unexplained flash of light, each mysterious cosmic tremor, could be the signature of a primordial black hole, a hidden piece of the universe's deepest secret finally revealing itself. Yet for all its elegance, this idea runs into some formidable cosmic roadblocks. The first comes from the oldest light we can see, the cosmic microwave background. This faint afterglow from the early universe is a pristine record, and it tells us the cosmos was remarkably smooth. Too many primordial black holes forming in that infancy would have churned space like a spoon stirring a pot, leaving scars and wrinkles in that light that we simply do not observe. Their potential for chaos is written in their absence. Then there is the testimony of the stars themselves. In dense regions like globular clusters, if dark matter were made of these ancient black holes, they would frequently disrupt the delicate gravitational dance of binary star systems, tearing them apart. We see these ancient binaries still gracefully orbiting, their survival a quiet argument against a universe teeming with a certain size of these invisible objects. Even the wide, loosely bound binary stars in our own galactic halo should have been ripped asunder by countless gravitational encounters, yet many remain intact. These observations have effectively slammed the door on primordial black holes, making up all of the dark matter across many possible mass ranges. So if not these ancient gravitational ghosts, then what is the invisible stuff that binds the galaxies? The current leading candidate is a sea of exotic, undiscovered particles, something that barely interacts with normal matter except through gravity. Think of it as a universe filled with an immense, intangible fog that weighs more than all the stars and planets we can see. This particle-based dark matter fits many observations beautifully, yet it too has its own mysteries, as decades of sensitive experiments have failed to directly detect a single one. This is why the primordial black hole theory refuses to die. It is a stubborn, elegant possibility that lives in the gaps in the mass windows not yet ruled out. The hunt has simply become more refined, more fascinating. Could a population of asteroid mass black holes have escaped our notice? Or what about planet-sized ones drifting in the emptiness between stars? The very difficulty of proving their existence as dark matter is what keeps this idea at the forefront of cosmic detective work, a tantalizing and contested clue in our greatest mystery. But if primordial black holes are not the dark matter, perhaps their cosmic role is even more dramatic. They could be the very seeds from which the most terrifying objects in the universe grew. At the heart of nearly every large galaxy, including our own Milky Way, sits a supermassive black hole, a monster weighing millions or even billions of times more than our Sun. And here lies a profound puzzle for astronomers. We see these giants in the very early universe, fully formed when the cosmos was still in its infancy. How did they get so big, so fast? A stellar mass black hole born from a dying star would take far too long to grow to such immense sizes. It is like trying to grow a giant redwood tree overnight from a tiny seed. The time just is not there. This is the supermassive black hole seed problem. Where did these colossal objects get such a massive head start? This is where primordial black holes offer an elegant and powerful solution. Imagine one of these ancient black holes, not the size of a mountain, but the mass of 1,000 suns forged in the first instance of time. It would be a ready-made heavyweight seed already lurking in the primordial darkness. When the first stars and galaxies began to coalesce, this massive seed would sit at the center of the action, a deep gravitational well that immediately began pulling in vast clouds of gas. Instead of starting from scratch, galaxy growth had a foundation, a pre-built anchor of immense gravity. With such a massive starting point, the process of accretion, of pulling in matter, could happen at a ferocious rate, allowing these seeds to balloon into the supermassive behemoths we observe in the early cosmos. They skipped the slow, initial steps. A stellar black hole would have to spend eons consuming material to reach even a fraction of that size, but a primordial seed was born with the mass and the authority to command its surroundings from day one. This theory elegantly connects the universe's violent birth to its present-day structure, suggesting that the giants ruling the centers of galaxies today are the direct descendants of the densest fluctuations in the newborn cosmos. It paints a picture where the largest structures we see are built upon the smallest, most dramatic imperfections from the beginning of everything. Far beyond the orbit of Neptune, in the cold, dark reaches of our solar system, a celestial mystery is unfolding. A handful of small, icy objects are dancing to a rhythm we cannot see, their orbits mysteriously clustered together as if being shepherded by an unseen force. Astronomers call this the Planet 9 hypothesis, suggesting a massive, undiscovered world is lurking out there. But what if this hidden shepherd is not a planet at all? What if it is a primordial black hole, no larger than a baseball yet holding the mass of Earth itself, left over from the dawn of creation? The gravitational effect would be identical to a planet, perfectly explaining the strange orbital alignments we observe. The key difference is one of substance. A planet is a physical object, a sphere of rock and ice you could, in theory, land on. This primordial black hole would be a pure knot of gravity, an invisible point of immense mass warping the space around it. You would not see it with a telescope, you would only feel its pull. This makes the hunt for it incredibly difficult and incredibly fascinating. How do you find an object that emits no light? Astronomers are proposing ingenious methods. One involves looking for brief, sharp flashes of light in the distant sky. If this ancient black hole were surrounded by a halo of dark matter, particles colliding within that halo could annihilate and produce gamma-ray signals we might detect. Another method relies on its extreme gravity. Should it ever pass in front of a background star, it would not just bend the starlight, it would create a distinct, rapid brightening, a telltale signature of a point-like mass. There is even a proposal for a fleet of tiny spacecraft that could sweep the outer solar system, feeling for the subtle tugs of its hidden gravity. The public allure of this idea is undeniable. It combines the familiar mystery of a hidden planet in our own backyard with the profound strangeness of a relic from the Big Bang. The thought that our solar system might secretly host one of the universe's most exotic objects, a fossil from the very beginning, transforms our cosmic neighborhood from a known quantity into a place of infinite, thrilling possibility. The silent collisions of these ancient relics send tremors through the cosmos itself. Our most sensitive instruments, the LIGO and Virgo observatories, have been listening to the universe ring with the echoes of black holes crashing together. Most of these events are attributed to stellar mass black holes, the end products of massive stars, but a growing number of detections feature objects that are puzzlingly heavy, falling into a mass gap where conventional stellar collapse struggles to explain them. This is where primordial black holes enter the stage with a compelling story. When two of these primordial objects formed in the universe's first chaotic second become gravitationally bound, they slowly spiral inward over billions of years. Their eventual merger is a cataclysm of pure gravity, rippling space-time with waves we can now measure. The key to their origin lies in the details of these collisions. Stellar black holes are forged in the fiery deaths of stars, a process that imposes certain limits and typically gives them a specific range of spins. Primordial black holes, born from the raw density of the early cosmos, would play by different rules. Their masses could be almost anything, including values that are strangely light or surprisingly heavy compared to their stellar cousins. A population of merging black holes with masses clustered in unexpected ranges, like tens of times the Sun's mass or in the elusive lower mass gaps, would be a powerful hint of their primordial nature. Even their spin tells a story. Many stellar black holes are expected to have significant spin from their parent star's rotation. A primordial black hole formed in a sudden gravitational collapse might have virtually no spin at all. When our detectors pick up a signal from a merger, the subtle fingerprints of mass and rotation are encoded in the gravitational waves. Finding a collection of black holes that are too heavy, too light, or spinning too slowly would be like discovering a new chapter in the universe's biography, one written not by dying stars but by the violent birth of space and time. Each chirp and ring down from a cosmic collision is not just a discovery, it is a message from the first second of everything, a direct line to the moment our reality began. These gravitational echoes from the first second could be more than just relics, they might be direct messages from the era of cosmic inflation. This was the moment the universe expanded at an unimaginable speed, far faster than light, smoothing and stretching the fabric of space. But what if this process was not perfectly smooth? What if there were tiny, intense wrinkles in that rapid expansion? According to some of the most advanced cosmological theories, these wrinkles are the key to creating primordial black holes. Imagine a single, powerful peak in the inflationary field, a moment where the energy driving the expansion suddenly surged. This surge would have created an extraordinarily dense region, a lump in the otherwise smooth infant cosmos. As inflation ended and the universe transitioned to a more sedate expansion, that ultra-dense lump would have immediately collapsed under its own immense gravity. It would not form a star or a planet. It would bypass all conventional physics and collapse directly into a black hole, a primordial one. This makes these objects far more than just ancient oddities. They become living fossils, probes of the physics that govern the universe's very first moments. Their existence and their specific masses would be a direct readout of the conditions during inflation. Finding a population of primordial black holes with a particular mass would be like finding a fingerprint, telling us exactly how powerful those inflationary wrinkles were. It is a cosmic detective story where the suspects are fundamental forces from the dawn of time, and the clues are these invisible gravitational traps. Could the same mechanism that blew up the universe also have sown it with these dark seeds? Each potential discovery of a primordial black hole is not just adding an object to our catalogs. It is a vote for a specific model of our cosmic origin, a tangible piece of evidence from a time before atoms, before light, when reality itself was taking its first breath. Our search for dark matter took a dramatic turn in the 1990s with a series of mysterious flickers in the sky. Two major experiments, one in France and one in the United States and Australia, were monitoring millions of stars in a nearby galaxy called the Large Magellanic Cloud. Their goal was to catch a rare celestial alignment. If a dark, massive object in our own galaxy's halo passed directly in front of one of those distant stars, its gravity would act as a lens, focusing the starlight and making the star temporarily brighten. They were not just looking for stars or planets. They were hunting for a hypothetical class of objects known as MACHO, an acronym for Massive Astrophysical Compact Halo Objects. The idea was simple. Perhaps the dark matter halo surrounding our Milky Way was not made of exotic particles, but of ordinary, albeit invisible, things. Think of rogue planets that never lit up, failed stars known as brown dwarfs or ancient cold white dwarfs, and at the top of the list of candidates were primordial black holes. For a few thrilling years, it seemed they had found them. The experiments did record a handful of these microlensing events. The star would brighten smoothly over several weeks and then fade away just as smoothly, a perfect signature of a compact, massive object drifting silently through the galactic halo. The number of events was too high to be explained by known stars. It pointed to a population of unseen MACHO making up a significant fraction of our galaxy's dark halo. Primordial black holes, especially those around the mass of a small planet, seemed like the perfect explanation. They were compact, dark, and exactly the kind of gravitational anchor the data suggested. The cosmic detective story appeared to be nearing its end, but science is a process of constant questioning. As more data came in from other observations, the initial excitement began to fade. The problem was one of numbers. If the galactic halo were teeming with enough planet-mass primordial black holes to account for all the microlensing events, they would have other noticeable effects. They would frequently disrupt the delicate, wide binary star systems that we observe peacefully orbiting in the halo. They would also subtly alter the precise motions of stars within nearby satellite galaxies, an effect that newer, more sensitive surveys failed to detect. The final blow came from the Hubble Space Telescope. It stared at the same star fields, searching for these microlensing events with even greater precision. It found far fewer events than the original ground-based experiments predicted. The conclusion became inescapable. While the MACHO observations did find something, likely a population of faint stars or white dwarfs, they could not account for all the dark matter. The window for primordial black holes as the sole explanation for the galactic halo's mass slammed shut for that specific mass range. The mystery of the MACHO events remains a pivotal chapter. It taught us how to hunt for the invisible, and it showed that the dark matter puzzle is far more complex than a single, simple solution. The hunt for primordial black holes did not end there. It simply evolved, moving on to other masses and other, even stranger possibilities. These ancient seeds of gravity may have done more than just anchor future galaxies. They could have lit the first fires in the cosmic dark. Before the first stars, the universe was a vast, featureless sea of hydrogen and helium gas. For stars to ignite, this gas needed to collapse into dense enough knots, a process that, according to standard models, should have taken a long, slow time. But the cosmos lit up faster than expected. How did those first brilliant suns switch on so soon? Primordial black holes provide a compelling answer. Think of them not as destructive vacuums, but as cosmic gathering points. Drifting through that primordial fog, each one was a tiny, intense gravitational nucleus. Wherever one of these objects passed, it would have pulled a cloak of dark matter and a swirling shroud of gas around itself. This created a ready-made density peak, a pre-packaged center for a star to form. Instead of gas slowly coalescing over eons, the process had a head start, a pre-existing deep well of gravity to fall into. This means the very first stars could have been born earlier, and they could have been far more massive than we ever thought possible. A stellar nursery built around a primordial black hole would be a violent, accelerated place. The infalling gas would have swirled in with tremendous energy, potentially forging stars hundreds of times more massive than our Sun. These colossal, short-lived stars would have lived fast and died furious, seeding the young cosmos with the first heavy elements in spectacular supernova explosions. Their brilliant, brief lives would have flooded the universe with its first ultraviolet light, ending the cosmic dark ages in a blaze of glory far sooner than anyone predicted. This theory reshapes our entire picture of cosmic dawn. It suggests that the first structures were not just clouds of gas, but clouds of gas with a hidden gravitational heart. The presence of these ancient black holes could have triggered a chain reaction of star formation, building the earliest proto-galaxies from the inside out. The universe did not just wake up slowly, it was jolted awake by the silent, persistent pull of its own primordial ghosts. The smallest of these ancient objects could be dying in a blaze of glory right now. While the giant primordial black holes persist, the tiniest ones, born with masses similar to a large mountain, are theorized to be evaporating through a process known as Hawking radiation. This is a purely quantum mechanical phenomenon, a dance of particles and antiparticles that plays out at the very edge of a black hole's gravitational grip. Normally, a particle-antiparticle pair will pop into existence and almost instantly annihilate each other. But if this happens right at the event horizon, one particle can fall in while the other escapes into space. From a distance, it looks as though the black hole is emitting radiation, slowly losing mass in the process. For a colossal black hole, this trickle of radiation is utterly insignificant. But for a tiny, mountain-mass primordial black hole that has been steadily evaporating for nearly 14 billion years, the final stages of its life would be anything but quiet. As it shrinks, the process accelerates in a runaway feedback loop. The evaporation rate skyrockets, and in its last second of existence, it would release an immense burst of energy, equivalent to the detonation of 1,000,001 megaton nuclear bombs. This final, violent death scream would flash across the universe as a brilliant, short-lived gamma-ray burst. Our telescopes are constantly scanning the skies for such high-energy events. Most are explained by colliding neutron stars or other cataclysms, but astronomers are on the lookout for bursts that do not fit the pattern, ones with a specific energy signature and no accompanying event in other wavelengths. Finding such a burst would be a monumental double discovery. It would be the first direct evidence for the existence of primordial black holes, confirming they were indeed forged in the Big Bang. At the same moment, it would provide stunning experimental proof for Stephen Hawking's most famous theoretical prediction, a concept that has never been observed directly. Every unexplained flash of gamma rays could be the last testament of a cosmic fossil, a tiny, ancient knot of space-time finally coming undone and revealing its secrets in a final, spectacular farewell. These final explosive moments could be contributing to a cosmic glow we have yet to fully explain. Across the entire sky, there is a persistent, faint drizzle of gamma radiation, the most energetic form of light. This diffuse gamma-ray background is not coming from any single point, but seems to emanate from everywhere at once. Its source has long been a mystery, often attributed to the combined light from countless distant active galaxies, their cores blazing with superheated material. But there is another, more exotic possibility. What if this universal hiss is the accumulated death cries of the smallest primordial black holes? The evaporation of a single mountain mass black hole produces a very specific burst of gamma rays with a distinct energy fingerprint. Now imagine that across the entire cosmos, across all of time, countless numbers of these tiny black holes have been reaching the end of their lives. Their final, simultaneous flashes would be lost in the vastness of space, but their collective, fading echoes would add up. They would blend together into a steady, all-pervasive whisper of high-energy light, a ghostly background static. This signal would have two key characteristics that make it a potential smoking gun. First is its spectrum, the precise distribution of energies within the light. The Hawking radiation from evaporating black holes predicts a very specific spectral shape, one that is difficult to replicate with other known astrophysical sources like active galactic nuclei. Second is its isotropy, meaning it should be incredibly smooth and uniform across the entire sky. Since primordial black holes would not be clustered in galaxies but spread evenly throughout the universe, their collective death should paint the cosmos with a perfectly even, faint gamma-ray glow. The challenge, and the reason we have not confirmed this yet, is the astronomical equivalent of isolating a single voice in a roaring stadium. The signal from these evaporations is weak and is completely Chinese letter by the brilliant, point-like gamma ray bursts from collapsing stars and the powerful jets from active galaxies. Disentangling this faint, smooth component from the brighter, clumpier foreground is one of the most delicate tasks in modern astrophysics. It requires meticulously mapping the entire gamma-ray sky and subtracting every known source looking for what remains. That faint, uniform residue could be the fossilized evidence of the universe's smallest, most ephemeral inhabitants. The universe's first few minutes were a furious nuclear forge, creating the lightest elements that would become the building blocks of everything to come. Hydrogen and helium were produced in vast amounts, matching our observations almost perfectly. Yet for one specific element, the math stubbornly refuses to align with reality. This is the cosmological lithium problem. Our most sophisticated models of the Big Bang's nuclear cooking predict about 3 times more lithium-7 in the universe than we actually see when we look at the oldest stars. For decades, this mismatch has been a persistent, quiet thorn in the side of cosmology. Something must have interfered with the nuclear chain reactions in that primordial cauldron. The answer might lie with the universe's earliest uninvited guests. What if primordial black holes were present during those first, fragile moments of element formation? Their influence would not have been through destruction, but through a subtle act of cosmic theft. The key player in this drama is the neutron. In the hot, dense soup of the early universe, neutrons were essential ingredients for building heavier nuclei. They would bind with protons to form deuterium, and that deuterium would then fuse into helium and eventually a small amount of lithium. But this entire chain is a delicate balancing act, highly sensitive to the number of available neutrons. Now picture a population of newly formed primordial black holes, each one a pinpoint of extreme gravity drifting through this nuclear plasma. As they move, they would have acted like microscopic sponges, selectively absorbing free neutrons right out of the surrounding soup. This is not because neutrons are special, but because they are neutral. Protons, being positively charged, would be repelled by the electromagnetic forces in the hot plasma, making it harder for them to fall in. Neutrons with no electric charge would slip through these electromagnetic barriers and be readily captured by a black hole's gravity. By siphoning away a portion of the free neutrons, these black holes would have subtly altered the recipe for the universe's first elements. With fewer neutrons available, the nuclear reactions that produce lithium-7 would have been starved of a key ingredient. The final yield of lithium would be lower, potentially bringing the theoretical predictions into a beautiful, precise alignment with the scant amounts we actually observe in ancient stellar atmospheres. This theory transforms primordial black holes from mere gravitational curiosities into active participants in the chemical destiny of the cosmos. They become the missing variable in a 70-year-old equation, the subtle saboteurs that resolved a nuclear imbalance at the dawn of time. Their ghostly presence in the first minutes could explain why the oldest stars carry a specific, lighter chemical signature, finally solving a problem that has puzzled astronomers for generations. The silent hum of gravitational wave detectors has delivered a puzzle that stellar evolution cannot solve. In 2019, the LIGO-Virgo collaboration detected an event labeled GW1921, a collision of two black holes that sent ripples through spacetime. The resulting black hole was an incredible 142 times the mass of our Sun, but the real mystery lay in the components. One of the merging black holes was about 85 solar masses. This number falls directly into what astronomers call the pair instability mass gap. According to our best models of how massive stars die, a star in a specific weight range between about 65 and 130 solar masses should not be able to form a black hole at all. Such a star becomes so hot in its final moments that its own light begins to create electron and positron pairs. This process robs the core of pressure, triggering a runaway thermonuclear explosion that utterly obliterates the star, leaving nothing behind. No star, no black hole. So how did an 85 solar mass black hole come to exist? It should be a cosmic impossibility. This is where the primordial black hole theory steps in with an elegant and powerful answer. Primordial black holes do not care about the life cycles of stars. They were not born from stellar collapse, but from the direct gravitational collapse of dense regions in the early universe. Their mass is not determined by a star's final breath, but by the size and density of that initial cosmic wrinkle. This means they can form with virtually any mass, including those that are strictly forbidden by the rules of stellar physics. An 85 solar mass black hole is not a problem for this model, it is a prediction. These ancient objects would naturally populate the mass gaps, filling the voids in our charts with relics from a time before stars even existed. The existence of such black holes, along with other puzzling mergers involving unexpectedly light or heavy objects, points to a dual population. Our universe's black holes are not all made the same way. Some are the children of dying stars playing by the rules of nuclear physics. Others are the elder siblings, the primordial ones, born from the raw energy of creation itself, and they operate under a completely different set of laws. Each gravitational wave signal from a mass gap event is not just a detection, it is a whisper from the dawn of time, telling us that the cosmos has more than one way to forge its darkest and most massive secrets. That unexplained flash of light from a dying black hole might have been part of a much larger cosmic-scale dawn. After the first stars flickered on, the universe faced its next great transformation, a period known as the epoch of reionization. For hundreds of millions of years, the cosmos was filled with a thick fog of neutral hydrogen gas. Then, something happened that flooded the universe with so much energetic radiation. It ripped the electrons away from these hydrogen atoms, turning the fog transparent and bathing everything in ionized plasma. The conventional story credits the first stars and galaxies for this monumental task, but what if their light was not enough? What if the true heroes of this cosmic clearing were the countless primordial black holes, each one glowing with the fierce energy of infalling matter? Imagine the early universe still dark and murky. A vast population of these ancient black holes would be drifting through the primordial gas. As they moved, their immense gravity would pull streams of hydrogen toward them. This gas would not fall in silently. It would spiral into an incredibly hot, bright disk around each black hole, a process called accretion. This furious friction heats the material to millions of degrees, causing it to glow with intense ultraviolet and X-ray radiation. Now multiply that single glowing point by trillions. The combined radiation from a vast number of accreting primordial black holes could have created a pervasive, all-directional bath of ionizing photons, a diffuse light that reached into every corner of the cosmos. This scenario offers a radically different picture from the standard model. In the standard view, reionization is a patchy process. The first stars and galaxies act like lighthouses in a vast sea, creating isolated, growing bubbles of ionized gas that eventually overlap. The radiation from accreting black holes, however, would be far more uniform. It would not come from distinct points, but from everywhere at once, like turning on a fluorescent light in a dark room instead of lighting individual candles. This fundamental difference leaves a distinct fingerprint that we might still detect today. The key signature lies in the faint radio signal from the neutral hydrogen itself, a specific wavelength of 21 centimeters. The pattern of that signal, imprinted when the universe was still in its infancy, would look dramatically different depending on what caused the reionization. The patchy, uneven process driven by stars would create a specific kind of fluctuation in this signal. The smooth, pervasive process driven by countless black holes would leave a much smoother, more uniform imprint. Our most powerful radio telescopes are now listening for this ancient whisper. When they finally detect the 21-centimeter signal from the cosmic dawn, its texture will tell a story. Will it show the clumpy signature of the first stellar cities, or will it reveal the smooth, universal glow of a cosmos lit from within by its most ancient and secretive inhabitants? The answer could rewrite the history of how our universe first learned to shine. The newborn universe might have undergone a violent change of state, like water freezing into ice. This concept, a first-order phase transition, suggests the fundamental forces themselves shifted in a sudden, dramatic fashion. Think of the cosmos not as a smoothly expanding fireball, but as a superheated liquid on the verge of boiling. In this seething energy, bubbles of a new, more stable phase of vacuum would have spontaneously formed and rapidly expanded. These bubbles were not empty. Their walls were immense concentrations of energy, sheets of high-density plasma racing outward at near light speed. As these bubbles grew, they inevitably collided. Where their ultra-dense walls met, the energy release would have been cataclysmic, far exceeding the most powerful particle collisions we can create. In these furious moments of impact, regions of space could have become so intensely dense that they collapsed directly into black holes. These would not be the random fluctuations of inflation, but something more structured, forged in the shockwaves of a universe rearranging its own most basic rules. These particular primordial black holes are like cosmic nuggets, dense fossils of a specific, violent event in the very first moments. Their potential mass would be directly tied to the physics of that phase transition. The energy scale of the shift, the speed of the bubble walls, all of it would be imprinted into the black holes it created. Finding a population of primordial black holes with a narrow range of masses could be the definitive evidence that such a cosmic metamorphosis truly occurred. This theory connects the existence of these ancient objects directly to the unification of forces, a time when electromagnetism and the nuclear forces were perhaps one and the same. They are not just remnants, they are relics from the moment the universe chose its fundamental character, a choice that was made not quietly, but in a thunderous, bubble-shaking climax that may have littered the cosmos with dark seeds. At the grandest scales, our universe is not a random scatter of galaxies but a vast, intricate tapestry, a cosmic web of filaments and voids stretching across billions of light years. This magnificent structure demands an original blueprint, a hidden framework upon which everything was built. The initial seeds for this cosmic architecture could have been a sprawling network of primordial black holes, woven through the infant universe like dark threads in a colossal loom. Think of the universe just after the Big Bang, a nearly smooth expanse of matter and energy. But if primordial black holes were already present, they would have created a subtle, pre-existing pattern of gravitational wells, a cosmic scaffolding. This framework was invisible, made of pure gravity, but it dictated the flow of everything that followed. Dark matter, the dominant but passive substance of the cosmos, would have been the first to respond. It began to drift toward these points of intensified gravity, pooling around each black hole and deepening the wells. This created a reinforced skeleton, an invisible mass structure that grew ever more pronounced. Then ordinary gas, the future material of stars and planets, followed this same gravitational map. It flowed along the filaments of dark matter, channeled by the underlying grid of primordial seeds. Over billions of years, this process sculpted the universe we observe, with galaxies and clusters forming at the intersections of this dark framework, like glittering dewdrops caught on the strands of a spider's web. The largest superclusters we see today may trace directly back to the densest knots in that primordial network. This theory offers a profound shift in perspective. The cosmic web was not born from a perfectly smooth beginning alone. It was imprinted, guided, and given its fundamental shape by the gravitational whispers of the universe's first and most enigmatic inhabitants, a dark foundation upon which all visible light now shines. Our galaxy is missing its neighbors. The most sophisticated supercomputer simulations of cosmic evolution paint a very specific picture of our cosmic neighborhood. They show the Milky Way should be surrounded by a bustling swarm of hundreds of small satellite galaxies, all held in place by the immense gravity of dark matter. But when we look up, we find only a few dozen. It is a glaring mismatch between theory and observation known as the missing satellites problem. Where did all the little galaxies go? The answer may lie not in the nature of dark matter, but in its texture. If dark matter were a smooth sea of invisible particles, it would clump together with incredible efficiency, creating countless tiny gravitational seeds for small galaxies to form. But if dark matter were instead made of primordial black holes, the story changes completely. These ancient objects would act like chunky gravel mixed into a fine sand. Their gravity is not smoothly distributed but concentrated into discrete, massive points. This fundamental difference in texture has a profound effect on galaxy formation. In the early universe, the gravitational pull from these heavy black holes would have stirred up the surrounding gas, creating chaotic, turbulent motions. This cosmic churning would have prevented the gas from cooling down and condensing into the small, fragile clumps needed to birth tiny satellite galaxies. It is like trying to build a delicate house of cards in a room with a constantly shaking floor. The larger structures, like the main Milky Way galaxy itself, had enough gravitational muscle to withstand this turbulence and form anyway. But the smallest potential galaxies were simply stirred out of existence before they could even get started. This process naturally suppresses the formation of the smallest satellites, leaving behind only the more robust, larger ones that we actually observe. The empty spaces in our galactic halo are not empty at all. They are the silent testament to a violent, churning youth, a period when the coarse, grainy nature of primordial black holes sculpted our galactic neighborhood by preventing the smallest stars from ever lighting up. Deep within the heart of our galaxy, a ghostly light has been shining for millions of years. Satellite-based telescopes have detected a persistent and very specific glow emanating from the galactic center. A stream of gamma rays all vibrating at precisely 511 kilo-electron volts. This is not a random energy. This specific signature is the unmistakable fingerprint of a positron, the antimatter counterpart of an electron meeting its end. When a positron collides with an ordinary electron, they annihilate each other in a flash of pure energy, producing two gamma-ray photons of exactly this energy. The core mystery is the source of all these positrons. Where are they coming from? Conventional explanations point to processes like radioactive decay from certain elements forged in supernova, or perhaps from microquasars. But the sheer abundance and distribution of this signal has never been fully explained by these known sources. There is another, far more exotic possibility drifting through the galactic core. What if the source is not a star or a remnant, but a population of dying primordial black holes? The smallest of these ancient objects, those with masses around that of a large asteroid, would be in their final, evaporative stages today thanks to Hawking radiation. This process does not just produce photons, it creates pairs of particles and antiparticles. For every electron that escapes the black hole's grip as it evaporates, a positron is also flung out into space. A single, small, evaporating black hole would be a faint fountain of antimatter. Now envision not one, but a vast, local concentration of these primordial black holes swarming the galactic center, a dense cloud of cosmic fossils all reaching the end of their lives at roughly the same time. Their collective evaporation would produce a steady, prolific rain of positrons. These newly born antimatter particles would not travel far. They would immediately encounter the dense clouds of gas and dust that also populate the galactic center, colliding with electrons and fulfilling their destiny in a burst of characteristic light. This theory elegantly explains the signal's persistence and its location. The galactic center is a region of immense gravitational pull, a natural trap that would have collected and held onto a large population of these heavy, ancient objects over the eons. Their synchronized death spirals would provide a continuous, abundant supply of positrons, perfectly accounting for the 511 kilo-electronvolt glow that has puzzled astronomers for so long. Finding definitive proof is the next challenge. It would require untangling this proposed signal from all the other astrophysical processes in that chaotic region. But if future observations can trace the antimatter flow directly back to seemingly empty patches of space, we may have found our culprit. The galaxy's most enigmatic light could be the final, fading breath of its oldest, darkest inhabitants. Deep within the heart of a black hole, our current laws of physics break down into nonsense. General relativity predicts a singularity, a point of infinite density where all matter is crushed into a volume of zero. But nature abhors an infinity, and many physicists believe a more complete theory, a theory of quantum gravity, must step in to prevent this cosmic catastrophe. This is where the concept of a Planck star emerges, a theoretical object that could replace the terrifying singularity. Imagine the collapse of a primordial black hole not ending in an infinitely dense point, but halting at the very final moment. The compression would stop at the Planck density, the maximum possible density allowed by quantum mechanics. The resulting object would be a Planck star, a fiery ball of exotic matter no larger than a single atom, yet containing the mass of an entire mountain or more. This is not a star as we know it, burning with nuclear fusion. It is a star in the quantum sense, a stable, ultra-dense remnant governed by the bizarre rules of the subatomic world. The existence of such an object is a direct prediction of theories like loop quantum gravity, which suggests that spacetime itself is woven from tiny, discrete loops. This granular structure of reality provides a fundamental repulsive force that becomes overwhelmingly powerful at the highest densities, putting the brakes on a complete gravitational collapse. The black hole's event horizon would still exist, hiding this incredible interior from our direct view. But the story does not end there. As the primordial black hole evaporates over billions of years via Hawking radiation, it slowly loses mass. In its final, explosive second, the event horizon would shrink away, and for a breathtakingly brief flash, the hidden Planck star within would be exposed to the universe. This sudden, violent release of its pent-up energy could imprint a unique signature onto the resulting gamma-ray burst, a specific pattern of light that our telescopes could potentially detect. Finding such a signal would be a discovery of unparalleled importance. It would not only confirm the existence of primordial black holes, but it would also provide our very first experimental glimpse into the realm of quantum gravity. We would finally know what happens at the center of a black hole, resolving one of the greatest paradoxes in modern physics and revealing that the universe's most feared objects are not endless pits of destruction, but are instead safeguarding a secret quantum heart. Some of the faintest galaxies in the cosmos are also the most mysterious. Scattered around the Milky Way are ultra-faint dwarf galaxies, collections of stars so dim and sparse they are barely visible against the blackness of space. Their existence is a puzzle. They contain very few stars, yet their motions reveal they are dominated by immense amounts of dark matter, far more than their faint light would suggest. How did these dark, ghostly islands form? The answer might lie with a single, ancient gravitational anchor. Imagine a small dark matter halo in the early universe, a cloud of invisible mass beginning to pull in traces of gas. According to standard theory, this gas should slowly cool, condense, and eventually ignite into stars, building a small but reasonably bright galaxy. But if a primordial black hole was present at the very center of that halo, the story changes dramatically. This black hole, a relic from the first second, would have acted as a powerful and disruptive engine. As gas fell inward, drawn by the black hole's intense gravity, it would have formed a swirling, superheated accretion disk. This process releases a torrent of energy, not in visible light, but in fierce X-rays and ultraviolet radiation. This radiation floods the tiny, fragile galaxy, heating the surrounding gas and preventing it from ever cooling down enough to collapse into new stars. The black hole effectively strangles its own galaxy in the cradle. It shuts down star formation almost before it can begin. The result is exactly what we observe, a galaxy that is overwhelmingly dark matter, with only a scant population of stars that managed to form in a brief window before the central engine switched on. These ultra-faint dwarfs are not failed galaxies, they are galaxies that were purposefully truncated. Their profound darkness is not a sign of weakness, but a fossil record of a potent internal force, a primordial black hole that has dictated its home's destiny for billions of years, leaving behind a ghostly imprint of what might have been. A sudden, brilliant flash of radio light can release more energy than our sun emits in 80 years, all in a fraction of a second. These fast radio bursts are one of the most energetic and least understood phenomena in the modern cosmos. Their origins are a subject of intense debate, ranging from magnetas to hypothetical alien civilizations. Yet one of the most compelling and violent explanations points back to the universe's oldest inhabitants. A cataclysmic encounter between a primordial black hole and a neutron star could generate the precise conditions for such an event. Picture a city-sized star, a neutron star, with a density so immense that a single teaspoon of its material would weigh billions of tons. Now imagine a primordial black hole, an invisible point of gravity with the mass of a planet, on a direct collision course with this stellar remnant. As the black hole closes in, its immense gravity would begin to shred the neutron star from the inside out. It would not just collide, it would plunge directly through, tearing the star apart in a process known as tidal disruption. The resulting chaos would be spectacular. The neutron star's incredibly powerful magnetic field would be violently twisted and reconfigured, reconnecting in an instant and releasing a staggering torrent of energy directly into the radio portion of the electromagnetic spectrum. This single catastrophic event would produce a fast radio burst of unparalleled power, a one-time scream from a dying star murdered by an ancient ghost. But collisions are not the only possibility. The final evaporation of the smallest primordial black holes, those with masses around 1 billion tons, could also be a culprit. As these objects explode in their final second via Hawking radiation, the resulting fireball of particles and radiation could interact with any surrounding plasma, generating a powerful shockwave. This shockwave, propagating through the magnetized interstellar medium, could itself produce a brilliant, transient pulse of radio waves. The key to linking these bursts to primordial black holes lies in their unique signatures. A burst born from a neutron star collision would be a one-off event, never repeating from that same location, and it might be accompanied by a faint, fading afterglow in other wavelengths like X-rays or gamma rays. An evaporation event, however, would be even more fleeting and might carry a specific polarization in its radio signal, a twist in the light that hints at the extreme physics of a quantum gravitational explosion. Finding a fast radio burst with these characteristics would be like finding a cosmic fingerprint at the scene of a crime. It would point directly to a perpetrator that is both ancient and invisible, suggesting that some of the most brilliant flashes in the sky are not the birth cries of new objects, but the death throes of the very first ones. Black holes are often described as the simplest objects in the universe. According to classical general relativity, a black hole can be completely defined by just 3 things: its mass, its electric charge, and its spin. Everything else, every detail about the matter that fell in, is permanently erased, lost behind the event horizon. This is the famous no-hair theorem, suggesting a black hole is a bald, featureless gravitational pit. But what if this cosmic barber shop rule is not the full story? The violent, exotic conditions of the early universe might have created primordial black holes with a permanent case of bedhead. The concept of black hole hair refers to any additional property that survives beyond mass, charge, and spin. For a primordial black hole, this hair could be a remnant of the unique physics present at its birth. In the seething energy of the first moments, fundamental quantum fields were likely intertwined with gravity in ways we do not yet fully understand. As a region of space collapsed to form a primordial black hole, it might have trapped a configuration of one of these fields, freezing it into place. This would be like a fossil preserving the atmospheric pressure of its formation. This hair would not be a physical substance sticking out. It would be an external field hovering just outside the event horizon, an invisible halo of information that subtly alters the geometry of spacetime around the black hole. One theoretical possibility involves a scalar field, a fundamental entity that gives particles their mass. If such a field had a specific value in that patch of the early universe, a forming primordial black hole could have locked it in, carrying that quantum signature for all time. Detecting this hair would require incredibly precise measurements. We would need to observe the gravitational waves from 2 primordial black holes merging and listen not just to the loud crash, but to the quiet, high-frequency ring-down that follows. The specific way a bald black hole vibrates as it settles into its new form is predictable, but a hairy black hole would ring differently. The presence of an external field would change the tone and decay rate of these spacetime vibrations, like the difference between striking a smooth bell and one with a complex engraving. Finding such a signature in a gravitational wave signal would be a revolution. It would be the first direct evidence that black holes are more complex than Einstein's theory predicts, that they can, in fact, retain a memory of their creation. This would shatter the classical no-hair theorem and force us to rewrite the textbooks, proving that the universe's most secretive objects carry a whisper of their origins with them, a hidden quantum diary from the dawn of time. The entire cosmos is humming with a low-frequency rumble, a chorus of gravitational waves that has been detected by listening to the universe's most precise natural clocks. Pulsar timing arrays have captured this background hum, a collective signal from countless merging supermassive black holes echoing throughout cosmic history. But what is generating this constant, low-frequency vibration of spacetime itself? The answer may lie with the very first seeds of gravity. A vast population of primordial black holes, born with the masses of thousands of suns, could have provided the foundational cores for these supermassive binaries. Imagine these ancient seeds sinking to the hearts of the earliest protogalaxies. When two such galaxies merged, their central primordial black holes would be drawn together, forming a binary system of immense mass from the very beginning. These pairs would then spiral inward over billions of years, their orbital dance emitting a steady stream of low-frequency gravitational waves. Because they formed so early and were so massive from the start, their mergers would be happening across all epochs of the universe, their collective signals overlapping to create the very hum we detect today. This primordial origin story solves a key puzzle. For pulsar timing arrays to detect such a strong signal, the cosmos must have been filled with an enormous number of merging supermassive black holes. A population of primordial seeds naturally provides that abundance, creating a dense network of heavy anchors that guarantees frequent, powerful mergers throughout time. The gravitational wave background is not a random noise. It is the integrated soundtrack of a universe built upon a dark framework of its oldest inhabitants, a continuous symphony conducted by the first and most enduring objects in existence. A star in a distant galaxy brightens for a single night, then fades back into obscurity. This brief, unremarkable flicker is one of hundreds detected by surveys like OGLE, the optical gravitational lensing experiment. While most microlensing events are predictable, a stubborn handful defy all classification. They are too short, too sharp, or their light curves are too asymmetrical to be explained by ordinary stars or planets. These anomalies are cosmic ghosts, and they point toward an invisible population of free-floating objects with immense gravity. Primordial black holes are the perfect culprits. Drifting alone in the darkness between stars, these ancient relics would act as perfect gravitational lenses. As one passes in front of a background star, its intense gravity warps the fabric of space, bending the starlight around it and creating a temporary, brilliant magnification. The unique signature of these events lies in their brevity and shape. A lensing event caused by a star lasts for weeks, but a primordial black hole with the mass of an asteroid could create a flash that peaks and vanishes in less than a day. Its gravity is so concentrated that the alignment must be nearly perfect to be seen at all. Even more telling is the light curve itself. A simple, spherical lens produces a smooth, symmetrical brightening. But if the primordial black hole is not alone, if it is orbited by a tiny, dense cluster of even smaller black holes or a faint halo of dark matter, the resulting light curve becomes distorted. It might have a sharp peak followed by a long, sloping tail, or a double-humped structure that betrays the complex gravitational field of the lens. These anomalous events are the fleeting shadows of the universe's first structures. They are not mistakes in the data, but messages. Each one is a potential sighting of a lonely wanderer from the dawn of time, a fossil so dark it reveals itself only by bending the light of something else. The hunt for these unexplained flashes is a meticulous census of the invisible, a search for the dark threads woven through the cosmic tapestry. The very fabric of space and time might not be a one-time event, but a single page in an infinite cosmic story. Some of the most profound theories in physics suggest our Big Bang was not the absolute beginning, but merely a violent transition from a previous state of the universe. In this breathtaking picture, a universe existed before ours, expanding, evolving, and eventually meeting its end in a great collapse or a fiery transformation that gave birth to our own cosmic dawn. And if that is true, then some primordial black holes could be the only survivors, the sole relics that made it through that ultimate cataclysm. They would not be just ancient, they would be truly immortal, carrying secrets from a reality that predates our own. In the framework of conformal cyclic cosmology proposed by physicist Roger Penrose, The universe goes through endless cycles or eons. Each one begins with a big bang and ends in an infinitely expanded empty state. But the mathematical bridge between the end of one eon and the beginning of the next allows for information to be transferred in a very specific form. Black holes, through their evaporation via Hawking radiation, can essentially encode their information onto the fabric of spacetime itself. A primordial black hole from a previous eon, evaporating completely as its universe died, could have imprinted its quantum signature onto the gravitational field that became the seed for a new black hole in our own universe. This new object would be a direct descendant, a cosmic echo of its predecessor. Another idea from string gas cosmology suggests our universe began as a hot, dense gas of the fundamental strings of reality. In that seething primordial soup, collisions could have created black holes directly, and some of those could have been stable remnants from a previous collapsed phase of the string gas. These would be literal fossils from the pre-geometric era, from a time before space-time as we know it even existed. What would such an object be like? It would be a time capsule, but not one you could open. Its event horizon would shroud information that obeys the physical laws of a universe with a completely different history, perhaps with different constants or even different dimensions. The pattern of gravitational waves emitted if two of these pre-Big Bang relics were to merge would be subtly different. They'd ring down a melody from a forgotten age. Finding one would be the ultimate archaeological dig, a journey not just to the beginning of our universe, but to a time before time itself. It would force us to rewrite the very first line of our cosmic history book, proving that our reality is just one chapter in an epic with no beginning and no end. Deep beneath the Antarctic ice, a cubic kilometer of pure ice is listening for ghosts. The Ice Cube Neutrino Observatory detects the faint flashes of light produced when nearly massless particles called neutrinos interact with the frozen water. These are not just any neutrinos, they are astrophysical neutrinos carrying energies millions of times greater than those produced in particle accelerators, and they arrive from deep space in a constant, mysterious drizzle. Their origin has been one of the great puzzles in high-energy astrophysics. What cosmic engines are powerful enough to create such elusive, energetic particles? The answer might be found in the silent, dark drift of primordial black holes. When even a modestly sized primordial black hole moves through a dense molecular cloud or the interstellar medium, its gravity pulls in surrounding gas. This gas does not fall in straight. It spirals into a furious, superheated disk, an accretion flow that generates intense magnetic fields and acts as a natural particle accelerator. Within this chaotic environment, protons can be accelerated to velocities approaching the speed of light, becoming cosmic rays of unimaginable energy. When these ultra-relativistic protons collide with other particles in the surrounding gas or radiation fields, they create a cascade of secondary particles, including pions. These pions then rapidly decay, and in that decay, they produce the very high-energy neutrinos that IceCube detects. A single, isolated primordial black hole would be a faint neutrino source. But the theory's power comes from their potential abundance. If the universe is filled with countless numbers of these ancient objects, each one a miniature, self-contained particle accelerator, their collective output could be immense. The combined neutrino flux from millions upon millions of accreting primordial black holes, scattered across every galaxy, would blend together into the diffuse astrophysical neutrino background that we observe. It would be a universal hum of creation and destruction, its source not in brilliant quasars or exploding stars, but in the quiet, pervasive glow of cosmic fossils. This transforms these black holes into what physicists call pevatrons, natural accelerators that can push particles to peta-electronvolt energies. The neutrinos they produce are the perfect messengers. Unlike charged cosmic rays, which are bent by magnetic fields, neutrinos travel in perfectly straight lines from their source. a future detection that could trace a high-energy neutrino back to a seemingly empty patch of sky, a place with no bright object visible, would be a compelling, if indirect, piece of evidence for a hidden, accreting black hole. The ghostly particles striking the Antarctic ice may be carrying a direct message from the universe's darkest and most numerous inhabitants, revealing that the emptiest spaces are alive with invisible, high-energy activity. The final theory catapults us beyond the boundaries of our own reality. The very existence of primordial black holes could be a scar, a permanent mark left by a collision between our universe and another. This idea emerges from the concept of the multiverse, a vast cosmic landscape where our universe is just one expanding bubble in an infinite, frothing sea of other universes. In this eternal inflation, new bubbles are constantly budding into existence, each with its own unique laws of physics. Sometimes these bubbles can collide. When our infant universe, still in its own inflationary phase, brushed against the wall of a neighboring cosmic bubble, the impact would have sent immense shockwaves rippling through the fabric of our spacetime. These shockwaves would have concentrated energy into incredibly dense, violent peaks, and in those peaks, matter and energy would have been squeezed beyond their limits, collapsing instantly not into stars but directly into black holes. These would not be random primordial black holes. They would be the direct children of a cosmic car crash, their specific masses and potential distribution a permanent record of that long-ago encounter. This transforms them from ancient relics into something far more profound. They become potential messengers, the only tangible evidence we could ever hope to find of a reality beyond our own. Finding a specific, unexplained population of primordial black holes, perhaps arranged in a vast, thin sheet or clustered with a distinct mass signature, would be like discovering a fossilized imprint of another universe on our own. It would be the closest we could ever come to observing the multiverse directly. These dark, silent objects would then hold the ultimate secret. They would be more than just the key to dark matter or the seeds of galaxies. They would be our only probes into the infinite, a permanent testament that our cosmos is not alone, but merely one page in a story without end. From dark matter to the cosmic dawn, and from the quantum heart of spacetime to echoes of other universes, these 25 theories reveal a universe built upon invisible foundations. The search for primordial black holes is far more than a hunt for exotic objects. It is a grand experiment, a way to test the most profound ideas in all of physics, from the nature of gravity to the possibility of a multiverse. Each unexplained flash of light, each mysterious ripple in spacetime, is a potential clue. The journey is just beginning, and the next great discovery could come from a new gravitational wave signal, a strange flicker in a telescope's data, or a revolutionary calculation. Stay curious, follow the science as it unfolds, and let us know which of these cosmic possibilities captures your imagination the most. Which theory do you think will be the first to be proven true?